This video presents supplementary material to our research article, A Terminal State Feasibility Governor for Real-Time Nonlinear Model Predictive Control over Arbitrary Horizons, including animations of its application to the safe and agile flight of a quadrotor aerial vehicle through an obstacle-covered environment. Model Predictive Control, or MPC, is the high-performance control strategy that defines a feedback policy by solving a receding horizon optimal control problem, or OCP, at every sampling instant. MPC has a broad application potential, as it can handle dynamical systems with input and state constraints. An MPC law takes the initial condition, x0, and computes an optimal and safe trajectory towards the desired reference R by minimizing a cost function while respecting constraints over a finite n-step horizon. The most used approach for ensuring a feasible control input can be computed each sampling instant is to incorporate terminal ingredients into the OCP, such as a terminal cost and a terminal set constraint. A terminal set constraint stating that at the end of the horizon, the terminal state xm should be in the invariant terminal set around the desired reference R, enforces stability and safety over an infinite horizon. However, if the reference R is chosen too far from the initial condition, or when the reference changes too abruptly, then the OCP becomes infeasible, meaning that there does not exist a safe and stable trajectory that can reach the terminal set within only n steps. The most common solution is to increase the MPC horizon, but this is often not possible in practice as it significantly increases the online computational cost. Other solutions modify the OCP in non-standard ways or modify the reference. These methods can lead to an increased offline and online computational cost, a need to have a priori and explicit representation of the constraints, the terminal set and the feasible set. Often, they don't come with theoretical guarantees and are mainly limited to linear systems. Our solution is based on modifying the reference without modifying the OCP, but by excluding the terminal set constraints in the OCP. Although this often means the terminal set can be reached, luckily there exists this green set of initial conditions, which is a subset of the MPC's feasible set in blue, from where the terminal set can be reached without enforcing the terminal set constraints in the OCP. Our solution does not require offline computations, only has a small increased online computational cost, does not require the constraints, a terminal set, nor the feasible set to be known, comes with theoretical guarantees, and can be applied to nonlinear systems. We propose a solution to the NMPC's infeasibility problem that can be efficiently applied to a wide range of systems that exhibit nonlinear dynamics and that are subject to pointwise-in-time constraints on their state and input variables. The main idea is based on a provably correct combination of the following methodological building blocks. 1. The OCP of the MPC law is solved over an arbitrary short prediction horizon without imposing the terminal set constraints. The NMPC prediction horizon is selected sufficiently short to allow real-time execution of the target computing platform. 2. A feasibility governor, or FG law, enlarges the region of attraction of the NMPC law by computing a feasible auxiliary reference signal V that is progressively moved toward the desired reference signal R. The proposed FG formulation relies on a discrete-time formulation of the continuous time explicit reference governor framework. This feasibility governor handles nonlinear constraint dynamics with a priori unknown non-convex constraints such as the red obstacles very efficiently. This is opposed to existing FGs which are limited to low-dimensional linear dynamics with a priori known constraints, as these schemes require feasible and/or terminal set computations which suffer from the curse of dimensionality. The proposed FG is composed of two parts. First, it computes in closed form a long horizon trajectory prediction of the terminal closed loop dynamics that ends near the auxiliary reference V. A minimal distance metric to predict constraint violation is also computed, and a direction that attracts the auxiliary reference V towards the desired reference R and repels it from obstacles. Second, a Lyapunov level set metric of a terminal energy constraint is computed at the end of the ERG prediction horizon to ensure stability and safety and hence feasibility not just over a long finite horizon but over an infinite horizon. The combined NMPC and FG algorithm is implemented in C++ and is validated by means of hardware-in-the-loop simulations of a nonlinear quadrotor area vehicle that needs to fly quickly and safely through an a priori unknown environment cluttered with spherical obstacles, while respecting additional constraints on its total thrust, its body torque, and its horizontal velocity. The blue spheres with the green reference frame denote a sequence of 3 distant desired set points that the quadrotor should track. The first 2 set points are steady-state admissible, and the last one is steady-state inadmissible as it is placed inside an obstacle. In the latter case, the closest steady-state admissible reference should be tracked. The orange moving reference frame depicts the auxiliary reference computed by our FG algorithm, which ensures feasibility. The NMPC law is implemented with an arbitrary short prediction horizon, varying between 5 and 60 prediction steps, depicted by the magenta dots. The FG is always computed for a long horizon of 100 prediction steps, depicted by the cyan dots. Both the FG's and the NMPC's prediction time steps as their sampling periods are set to 50 milliseconds, which is sufficient for real-time execution. It is worth noting that the direct or ungoverned tracking of these distant set points, so without our feasibility governor, is computationally intractable, even for large terminal set sizes. Here, the effect of different NMPC prediction horizons on closed-loop performance is demonstrated. One can observe that independently of the horizon length n, a feasible trajectory that ends near the auxiliary reference is computed, resulting in stable and safe flight. Moreover, as n is increased, the closed-loop performance improves in terms of horizon settling time and results in a reduction of the cumulative closed-loop cost. For the longest horizon of 60 steps, the quadrotor is extremely agile, showing tilt angles exceeding 90 degrees. It passes very close to the obstacles and reaches the target first. For the intermediate and short horizons of 15 and 5 steps respectively, the quadrotor shows less aggressive performance. This is because there is a larger part of a trajectory prediction dominated by the feasibility governor, which will reduce the dynamic safety margin and as such the velocity of the auxiliary reference, when the prediction of the terminal closed-loop dynamics is close to obstacles or other constraints. This FG method relies on a discrete-time implementation of a continuous time ERG law and is based on integrating the auxiliary reference velocity with a time-varying step length, which is reduced with a fixed reduction rate whenever the auxiliary reference guess results in a trajectory that is steady-state or dynamically inadmissible. If it is admissible, the scaling factor can be increased again to possibly speed up conversions at the next sampling instant. We also demonstrate the effect of different NMPC prediction horizons on the computational time. Clearly, the desired performance gain must be paid by an increased computational time. In the computational time graphs, we can observe small peaks of 30 milliseconds for an horizon of 5 and large peaks of 200 milliseconds for an horizon of 15. The latter drastically exceeds the real-time requirements of 50 milliseconds. To allow real-time execution, one should go for the short horizon NMPC of 5, for which the average computational time of both the short horizon NMPC and the long horizon FG are very low, about 5 milliseconds. We can conclude that the FG adds little additional online computational cost compared to the significantly more computationally expensive NMPC.